Where 2 minutes? We wait for okay, Julian, are you ready? Ah, ready? We should wait. We should wait. Let's wait. 3 minutes. Okay. So we can chat. Okay. Just the category level is one. So much all reason. Everything is over full of tourist reason. And this place is full of tourists. Nevertheless, it is, I mean, it's something still original. That's very quite cold. So, the room is quite cold. This I don't know. This, I mean, I'm a cold there. Yeah. The point is that is quite safe from tourists because it's different. I mean, if you don't know where is it, you are not able to find it. It's on the line. We know, but the street is not very. Do you say exactly your name? Dmytro? No.
Dima.
Dima. Ah, it's in there.
Yes.
And the accent is on the O or?
On I.
Volin.
Ah, Volin.
Volin?
Yes. On O.
On O.
So don't use French.
Okay.
Yes. No. No. No.
So let me introduce the speaker, the second speaker of this afternoon session. So the speaker is Dmytro Volin from Sweden, I guess.
Yes.
I don't know exactly the name of the university, but it's Uppsala University, sorry. So it will speak about geometry of Bethe algebras from ODE IM.
Yes, thank you. So I decided to make title coherent with the subject of the conference, and I promised to use an ODE, very concrete, but one, and to derive some geometry. And for me, geometry will be the one which I call fused flags. And this I will try to sell to you. It's not official mathematical terminology, but I hope at least you know what flags are. Flag. So flag in mathematics is a sequence of embeddings, line into plane, plane into three-dimensional plane, and so on. So this is a good mathematical flag. This is also good mathematical flag. And now somehow in this talk, we're going to fuse them together to get to geographical flags. So flag of Sweden works. So presumably you have to work in such country to decide on this name. Early version of this slide had Union Jack, but you know, Brexit and so on. So yeah. So let's stick to Sweden. Okay. There are many ways to motivate what is happening. And I decided to pick Hirota equations, bilinear Hirota equations, an example. There are many other ways to do introduction. So what is Hirota equations? You have some kind of a lattice. In the vertical direction, you take your favorite Dynkin diagram. For the simplicity of this talk, everything will be simply laced. So formulas honestly only work for simply laced. Otherwise, well, we not go there too much. And in the horizontal direction, it's basically infinite in both directions, or semi-infinite. And they have discrete indices. A labels nodes of the Dynkin diagram. So it's not exactly vertical, it's whatever the diagram is. And S is just integer. And the equation is it possible to? Yeah. So the equation is the following one. So we have a function t, which depends on some variable called spectral parameter. And all functions will be functions of spectral parameter, and we consider discrete shifts. So this bracket n means that we shift by n units of h/2, h any number you want, it doesn't really matter. And plus minus is the condensed notation where we do the minimal possible shift. And so t depends on spectral parameter and evaluated at node as shifted by plus times evaluated at node as shifted by minus equals this product. So t in there to the right and to the left of the corresponding node times t at all adjacent nodes of the Dynkin diagram. So usually it's quadratic. First time it was A series, that's why it's called bilinear equation. Everything is quadratic, but in this bifurcation node it will be cubic. But it's okay. It's okay. And this equation appears in many different applications. If you do integrable relativistic field theory or not relativistic, you do something called thermodynamic data ansatz. Then you get what is called Y system, and from there you get to T system, and you get this equation. This is one option. In case you do your geometers, maybe you like cluster algebras, or for any other reason you like cluster algebra. Well, you can think about this kind of some kind of a quiver, and this is if you put t minus on the right hand side, it's a typical mutation relation. And you can you can ask question about mutations, and actually, if you go back to Y system, what we do here can be used to, for instance, understand the homologic of periodicity. This is goes there as well, and then like a lot of application integrability. If you want to go abstract direction, you take quantum affine algebra, do Differentiation models, and there is something called Q characters. Well, this has meaning of Q characters, and this is relations between them. If you want to make it less formal, then Q characters becomes quite explicit transfer matrices for integrable spin chains. And Andrea Raimondo's talk gave us another example. So he did only SL2. So there are no indices A and S. He had just one T. But yeah, so this is another example. All generation for higher ranks will get the T's as transfer matrices and all type of ODM correspondences. So this equation is universal. And yeah, and message I would like to give now is that combinatorics of the equation is always the same. It never changes, more or less. What differs between different applications is what analytic properties you consider about these functions. There are examples like from TBA or for ODM, then these T functions are entire functions spectral parameter. There are examples that if these functions are polynomial times a factor which has a puncture as the origin. There are examples from IDS-CFT correspondence when these functions have branch points. And it can be also formal variables, right? You do not need to even think about them as function. You can consider just this is after all a discrete system, right? So you can consider them as just elements of formal polynomial or fractional ring, for polynomial ring or fractional field, and just operate formally. So combinatorics in all this example is the same. If you want to do some physics, then you have to tell later what analytic properties are. And these talks will be mostly about combinatoric, and strategies we are going to do is that we are going to use ODM to guess what combinatoric should be, so very concrete analytic situation, and then apply it to something else. And I will announce one of the results because I decided to use this motivation. There will be Q functions, Baxter Q functions, which assemble in a certain way. And using these Q functions, we are able to solve these equations. So notice that this is infinite system of relation and infinite system of an infinite number of functions. So it can be, I will explain this formula later, it can be parameterized through finite number of functions, which eventually are related to Baxter Q functions, but in some very complicated extended way. So I also did some mistake. No, I'm fine. Okay. Okay. So technology that we are going to use, actually by Mazera Raimonda Valerie mostly, but we will do some new way to use it. Okay, so here's the plan. When I look at the speakers, I notice that you do some kind of differential equations, and maybe it's a good time to spend some time on the algebras. It will be good complement to all other talks. This was my impression. At least after Andreas' talk, I say, yes, I did the right choice, because I will spend much less time on linear problem, because actually it's beautifully explained in many talks, including Andreas. So first we are going to review what are flag manifolds, how it's related to representation theory of the algebras. And then we see how they appear in the complete ODE, ODE differential equations. And then we solve Hirota, as promised. And then I explain how to use this technology to something else. This is what I'm going to do today. Okay, so let us start. Well, so G will be simply algebra. Minimum information we need to have to pick a Cartan subalgebra. And alpha A will denote its simpler roots. E and F will be corresponding raising Lovren operators. So the algebra it have typical decomposition into Lovren part, Cartan and raising part. We also will need to do co-roots, so they're given by this formula. But conceptually, what they are, the element of Cartan subalgebra as opposed to simple roots themselves, which are elements of the dual space. And using co-roots, we introduce dual bases. So co-roots and co-roots form bases on corresponding vector spaces. And omega is a form of basis that is dual to alpha check. It's called fundamental weights. So why we need fundamental weights? Well, because we need some basic knowledge from representation theory, that if you take our algebra, you consider finite dimensional representation of weight omega, that's uniquely characterized by highest weight. So highest weight is characterized by the property that all raising operator are annihilated, and all Chevalier generators from Cartan algebra acting highest weight produce as integers called Dynkin labels. And so the highest weight being expanded on the basis of fundamental weights with these integers. So this is basic data you need to know. And what we're interested in. So actually, so our representation space is a vector space, but we are going to projectivize this. What it means, if you take vector in the corresponding representation, we decompose in the some weight basis. So C will be coefficients of decomposition, and we consider the coefficient as homogeneous coordinates on the corresponding projective space. So dimension of the space is dimension of representation -1. So we consider this projective manifold, so everything up to a scaling in this talk. And in particular, we agreed that the first basis vector in this expansion is actually highest weight state for the corresponding representation. So 0.1000 is like somehow distinguished in this notation. And we would like to study action of Lie group, I mean, connected component of identity corresponding to Lie algebra. So corresponding to Lie group, how it acts on this space. So important to notice this action is not free. So if you take highest weight state as our point, because raising operator kill it and Cartan just rescale it, from the point of projective space, highest weight action of n plus h is stabilizer already. And then also from Lovren operators, if Dynkin label is 0, then corresponding Lovren operator also kills the highest weight state. So this is an ensemble of all generators in the algebra who actually do not change highest weight state. Either put it to 0 or just rescale it. So define now by set A all indices such that Dynkin label is non-zero, and consider exponentiation of raising part of the algebra, Cartan algebra, and everything generated by Lovren operator by commutation, generated by commutation relations times answer relations, such that Dynkin labels are 0. This is what I'm writing here. So these are all guys who actually, for whom highest weight state is a stability point. So we do exponentiation. What we get, we're going to call PA, and this is what is known as parabolic subgroup. One possible definition of parabolic subgroup is basically any group that contains Borel subgroup as Borel is a subgroup. And parabolic subgroup will be stability group of our highest weight. And G-orbit by standard theorem is just G quotient by stability group. And this is what is known as partial Fleck manifold. This construction is true for any algebras. Original names, of course, coming from SLN case. And the second thing which is important to realize is that G action is actually not transitive. So you cannot obtain all possible points in the space by acting with your group on the highest weight. And if you only study n by n matrices acting on the column 1, 0, 0, 0, you know that n by n matrix acting on 1, 0, 0, 0 produce you everything. So this is basically the only exception from the statement. But in all other situation, the action is not transitive. You cannot get everything. And it's important to realize. I will give you now some examples that you really feel why it's so. So the first example is A-series algebras. So this is our Dynkin diagram. And let's consider second fundamental representation. So it's Dynkin label 0, 1, and everybody here is 0. So this fundamental representation is just 2 forms. Yes. So dimension of this representation is n choose 2 when n is size of your matrices. And highest weight state is E1, which E2 in the standard basis. Like if you take standard basis, E1, E2, E3, and so on. So E1, which E2 will be highest weight state in this representation. Arbitrary vector will be sum over 2 forms in the standard basis of exterior powers of the standard basis. So important message here that this guy is actually plane spanned by 2 lines. So no, it's true, you should know very well probably that not arbitrary to form it represents for you a plane. So if you take arbitrary to form, it will be not a plane. What you want that to form which itself is 0. This is called Plücker relation. So this is example of just taking projective coordinates on the space called Plücker coordinates and considering Plücker quadrics. This is how you can construct this partial Fleck. In this case, it's called Graspanian. So it's space of all possible 2-dimensional planes passing through the origin. And in general, if you take A's fundamental representation and do the same game, your Graspanian will be, you just guess A's Graspanian on an n-dimensional vector space. So for SLN case, each node is this is just vectors. This is 2 forms, 3 forms, 4 forms, and being on the orbit of highest weight vector means that this form actually defines corresponding hyperplane. How we encode this information by putting Plücker relations on top. They're all quadratic, actually. Yeah? Okay, so this is example when we took fundamental representation, when we took just 1 fundamental weight, which is non-zero. Everybody else is 0. Let us do the opposite case. Let's take, we call it like well representation. Let's take our weight omega being sum of all fundamental weights. So Dynkin labels is 1 everywhere. And in this case, highest weight state in this very big representation is actually E1 for the first node, E1 which E2 is the second node, E1 which E2 which is in the third node. So this is line embedded into plane, embedded in the third plane, so on. This is example of the complete Fleck. And a G-orbit of it just start rotating these things, but of course doesn't change the fact that the rotated stuff embedded is one another. So that's how you get what is called maximal Fleck manifold. This is precisely G quotient B, where B is the stability group of the sequence. Yeah. You have any questions here? Huh? B is Borel. B is Borel, yes. Yeah. And right, and this is one way of doing maximal Fleck. Consider this representation this weight, but instead we also can consider tensor product of all fundamental. So this tensor product is not irreducible representation; it's reducible. It contains this representation is sub-representation, but from the point of view stability group, it doesn't matter and doesn't really matter. We just take tensor product of this highest weight space from here. It has the same thing, but Borel will be still its stability, and we still make the same orbit. So instead of doing this irreducible representation, it's better to consider this collection of one form, two form, and so on, and make just what is called degree embedding. So this via Grassmannians, we take cross product, Cartesian product of all Grassmannians, and inside Grassmannian we can find maximal flux, which is orbit of highest weight. This is actually how we will proceed. This example is more standard to think about, but in practical usage we have to extend our representation to tensor product of representation.
And what's saying that you want to consider products of Grassmannians?
Yes.
Then imposed by this embedding incidence relations. I mean, with one space is containing those ones.
So what I'm saying within the product of Grassmannian, I consider it's a big projective space by degree embedding. What I'm saying is that I can find product of highest weight for each Grassmannian, and orbit of this product of highest weight will be maximal flux. Yeah. So I take a highest weight here, highest weight here, highest weight here, and common orbit of everything will be this space. So
what's the advantage of doing this approach? Maybe you will explain.
For us, because for this approach, we basically everything will be written as Pluke relations. So here it's a little bit hard, but here we can just use the same Pluke relation plus Pluke relation, saying that they live on the same orbit. So in this approach, writing a Pluke relation is much more covariant and easy to do. This is an advantage. Okay, so this is how things are looking for a SLN case. And I will say just a few words about D series. So in the for D series, what changes that so this first node is a vector representation, and what changes that now E1 is still its highest weight, but now the basis vector is E plus minus 1, E plus minus 2, and so on. And by this diagonal Cartan are actually null vectors. In the case of orthogonal group, we have scalar product, and we can compute bilinear form for vectors, and all these vectors are actually null. So in particular, highest weight is null. Yeah. So it's like light cone in physics. And of course, the orbit of null vector will always stay like null vector. So if you look at this flux construction, here we have vectors, yes, so C embedded in the bigger space, but these vectors are all null. This is would be Grassmannian equivalent G quotient P1 for D series. This C is embedded in C2 in the same way. C2 is again is what is called isotropic space. In all possible directions, these are null directions and so on. And at the variant, we have split. So we have actually go to the half of the dimension. So we have SO2R. We came to the half of the dimension of the spaces. And there actually we have self and anti-self dual representations. So these are still isotropic spaces, but we have self-dual isotropic spaces as anti-self dual isotropic spaces. And how they look like, how straight for self-dual look like wedge of all E's with pluses, and for anti-self-dual wedge of all E's with 1 minus. So they form two different reducible representations to different orbits that corresponding to this bifurcation happens here. And so this is the structure of the maximal flux and partial Grassmannians for D series. Any questions here? Okay, so let us make summary. So if we take highest weight in the eighth fundamental representation, the orbit will be what is called Grassmannian manifold, G quotient by PA, when PA is one of the maximal parabolic subgroups. If we take tensor product of all possible fundamental highest weights, then stability group of this guy is Borel, and so the orbit is maximal flux G quotient B. And we actually using this homogeneous coordinate description of the spaces and use Pluke relations or generalizations of them to fix this internal orbits. And so this is how we describe the spaces. Let us discuss how it's related to linear problem. So we consider this linear problem. So we psi is a vector in some representation of Lie algebra, which depends on one complex parameter. So in this talk, complex parameter is x. So D is just Dirac differential in X, and A is flat connection, it's holomorphic connection, whose explicit form is the following one. So in Andrea's talk, L, you have to put L equal to 0 and know this monsters, N is not 0. So the simplest example. And so the sum of all raising operators associated to simple roots, and also we add here a affine root. So what is affine root? It's actually lowering operator corresponding to the highest weight of your adjoint representation. So in the case of SL3, so this is E1, this is E2, and T0 is this guy. So this connection is called affine opera, except that we already affine direction we already put in evaluation representation, so not really affine left.
Okay.
Yeah, I see. It's yeah. Okay. So this is the standard connection, the same one which was in the rate of tail, and it goes back. So we just take this particular opera, and why we have group function all over the place? Well, because if you try to solve this equation, well, C at point X is parallel transport of X0 using P exponent, right? And this is element of our group acting on given representation. So better we know if this point is somewhere, what is its orbit under EG action. And of course, my goal will be to show that if you consider good solutions, actually we'll be on this flat manifold orbits all the time. This is actually the point. Okay, so some notations. So before we have roots and their dual basis was fundamental weights. Likewise, we can take roots and make their dual basis called coveights. Sum of all coveights, what is called well collector, it's element of Cartan algebra. The only thing we need to know about it is that this element commutes with raising operator associated to simple roots in this way, and with this affine operator, it commutes with 1 minus h factor, and h is called Coxeter number. It's just some number. Later I will show you some picture, but for the moment, some number. And because of this commutation relation, you can show that if psi is a function of x and z, so in Andrea's talk, z was called E. So if psi as a function of x, z solves the linear problem, then this combination, substituting this change of variable for x and z and some prefactor, which is exponent of Cartan algebra, so group element acting on psi. So this is another solution of our linear problem. This is what is called semantic rotation. It somehow, for me, it alludes to some renorm group equation if you go back far away in physics, but maybe I'm wrong for historical reason. For me, semantic is a renorm group guy. Is it the same guy or not? Because okay, so it's come back.
So we know where they
Yeah. Okay, so it's for due to Andrei Vorovson. Okay. Okay. So I was thinking about this. I can vaguely argue that this is RG equation. But yeah, so historically it's called semantic rotation. Thank you for explanation. Why? So what happens if you have one solution, we can get another solution. And so how many solutions do we want? Well, number of solutions in linearly independent solution is dimension of representations that we chose. And here there is this number m. We assume is m is big enough. So but we can do this rotation as many times as we want to get actually the basis and solutions, although we will not do this in practice. But just a comment aside, so potential has x to the power of Coxeter number multiplied by m. M should be just a big number, big enough to not have monodromy around. So this rotation slowly shifts x in the complex plane. If m is big enough, we never make the full circle around. This is what we really, the only thing we really need. Yeah, so you see that Q depends is M's plus 1's rules of unity, and we just do not want to make the full circle. Then we are good. Okay. Okay, and then what we want to do, we want to go to infinity, and at that infinity we can do WKB analysis, and there is Stokes phenomena, and we can find explicit solutions. This is exactly when I decided to skip and just give you the answer. So how it looks like? First, we introduce quasi-momentums. This is our potential to the power 1 divided by Coxeter number. So in the case of SL2, Coxeter number is 2, just a square root of potential. It's normal momentum in physics. And then we introduce action variable, so integral of quasi-momentum. And in terms of action variable, our solution, and x approaches infinity, has a following structure. First, p to the power minus rho check. So I remind you that rho check is element of Cartan subalgebra. So it's some group element. It's said just to make things nice. It's not really too important to focus on it in this talk. And then we have exponent of minus mu. Mu is a number. S is this action variable. So S is a function of x in this way. And then we also have vector, which is a constant vector, which doesn't depend on x. So mu and u mu solve eigenvalue problem for the following operator. So this operator sum from 0 to r of all EA operators, now with 0 included. For SL3 example, this is this cyclic permutation matrix. Yeah. So for this matrix, it's very easy to see that eigenvalues will be exponent of 2 pi I divided by h. Coxeter number for SL3 is 3. So third root of unities are all possible third root of units are eigenvalues of this matrix. This is obvious. But in general statement is the following one. So if mu and u mu solves this eigenvalue problem, then kind of semantic rotation, namely multiplication of mu by factor gamma, which is h root of unity, and taking the corresponding eigenvector, is also solving eigensystem. And so how eigenvalues look like? So what is the meaning of eigenvalues of lambda? Well, when you speak about the algebras, you have weights, and weights are just points in a dual space to Coxeter algebra. And then there is something called Coxeter plane. It is Coxeter plane is two-dimensional space inside two-dimensional vector space within weights space, and this space is very special. It's space on which Coxeter element acts by rotation by angle 2 pi divided by h. And all the pictures that you see on Wikipedia about group theory and Lie algebra, you always see this picture. So this picture is actually projection of all weights in the adjoint representation of E8 to the Coxeter plane. So I just copy pasted it from Wikipedia. So Coxeter number for E8 is 30. So there are 30 points here. And this is angle is 2 pi divided by Coxeter number. And every time we multiply by gamma, we rotate it in the same way. This is how spectrum of lambda is organized. You just have to replace E8 with your favorite algebra and replace a joint representation with your favorite representation. This will change the picture. So how this compared to the linear problem? So remind about semantic rotation. So semantic rotation has a fully nice property. Okay, first of all, I forgot to say, so if you look at this expression, if x goes to plus infinity like here, right, then this number is positive. And if you take mu, the largest real number possible, so we pick this eigenvalue, we'll construct the fastest decreasing solution. Out 250 something number of solutions for adjoint of 8, we have to pick the fastest decreasing solution. This is uniquely fixed by this property, solution in that particular direction. But this is only true in certain Stokes sector. So let's say this one. Picture is qualitative. And so rotation, semantic rotation by one sector, precisely should be compensated by one rotation in the complex numbers. So we can translate Stokes semantic rotation of this solution to just rotating eigenvalues in the complex plane. So this representation theory give us very good control on asymptotic behavior solution to linear problem. And now I am able to make first claim. And for this one, I can even say the word theorem, honestly, and do not believe I missed something. So first, we need to introduce something which we call height function. So let us draw our Dynkin diagram in 2 dimensions. Every time we go to the next node, we are allowed to go either up by an integer or up by an integer, exactly by 1. So if so, P is the height of this node, and if 2 nodes are adjacent to the Dynkin diagram, we impose condition that the difference plus or minus 1. This is called Coxeter. I mean, we call it height function or Coxeter height function, and then let's consider incidence matrix of the Dynkin graph, and consider eigenvector of this matrix with this eigenvalue. Gamma is H's root of unity. So if you know Perron-Frobenius series, this is Perron-Frobenius eigenvector. All the mu's will be positive reals. You can normalize in some way you want. And then, actually, the statement is the following one, that mu A, so mu A, which is one of these numbers, times H root of unity to the power P, where P is the Coxeter height function, will be actually eigenvalue of this matrix lambda in representation A. This is some statement, and we define the corresponding eigenvector. So eigenvector of matrix lambda is the representation A rotated by amount of P. This is how notation is defined. So using this data, we allow to parameterize very important vectors. And there is a theorem which you can prove that if P is a height function as described here, the tensor product of this eigenvector, so we take tensor product of all possible fundamental representation. This tensor product becomes highest weight state for certain choice of Cartan and Borel subalgebras. This is a theorem. How you prove it? First, you have to open this paper, read it carefully, and then you have to do a little bit of updates, and then it works. So this is fact that we can choose any P. So with this constraint is the crucial what I'm going to say next. Okay, do you have any questions so far? So among all possible eigenvectors of this matrix lambda, we pick up very specific ones, which actually correspond to the smallest solution in certain directions, hence uniquely fixed in this way, and be able to prove that they actually highest weight in the standard product of fundamental representations. So this is mathematical fact from representation theory. And now we consider a monodromy from infinity to the origin. So let's take a solution and, sorry, there is a mistake here. Let's define finally Q vector. So Q is a vector in the eighth fundamental representation, which depends only on parameter Z. And how it's defined? Some group factor, which there to make things nice, times psi evaluated at the origin. This is a mistake on the slides, evaluated at the origin. So we take solution of linear problem and evaluate it at the origin. And what we want to do, we want to start at infinity, where we have control because of WKB, and take the monodromy using P exponent to the origin. And at the origin, evaluating solution at the origin, we get what we call Q vector. And the definition is such that semantic rotation for these Q vectors is just a shifting of Z by multiplication of Z by a factor of Q. And corollary of this statement, which has some subtlety when you prove, it's not obvious, not immediate. There is some resurgence playing the game, but more or less it's possible to do. So for any height function, if you take the tensor product follows the Q function shifted by P, which at the denote Gothic Q shifted by height function P, it's actually belong to this maximal Flack manifold. So what conceptually or informally, what is happening at infinity, we take this solution, which we know by theorem is highest weight in the corresponding Cartan and Borel solution. Then we do some stuff and do monodromy from infinity to 0, do some stuff again. Every time it's action of group element, and we arrive here. This is logic. If you try to make it precise, we have to sit down with you carefully. So in reality, I only can say modular Borel subgroup action because of some Stokes phenomena, but the fact that it is in group orbit is true. So this is the main conclusion, that we can construct such Q vectors. And now let us formalize it for the sake of everything happens next. We come back to the beginning of my talk and make some universal definitions. So first of all, we introduce space of spectral parameter. So generically is a set that admits reaction of some translation group. So two examples. It's either a translation, additive translation or multiplicative translation. If you do ODM case, it will be multiplicative translation. But if you do exponent of z, z is exponent of u, you get to additive, right? So f with brackets n means pull back through this translation. And then we define the notion of fuse flag. So fuse flag is a map from this space to tensor product of all fundamental representations, such that for any height function, so function that has this feature, Q shifted by the height function belongs to the g-orbit of the highest weight. So it's a maximal flag. And the most important place here is the word all. So this map doesn't depend on P, but whenever P is height function, this property should be satisfied. And this is non-trivial part of the story. Of course, you can cook up some vectors that have this property for one choice of P. But cooking up vectors that for any choice of P still have the property is quite far non-trivial. So this is what is called fuse flag. And as shown now, discussed linear problem can be used to construct the full fuse flag. Just explicit spectral determinants in the linear problem form this fuse flag in the way explained. And this is a summary of part 2. Yes?
This is still dependent on the spectral variables.
Yes, yes. So Q will be functions of spectral parameter, yes.
What is sigma?
Sigma is space of spectral parameter.
Okay. Oh, okay, and there's an action which may be multiplicative or additive.
Yes, yes, yes. So ODM correspondence or linear problem allowed us to see that this is actually possible. Moreover, it showed that it is nice construction to do, which turned out to be correct at the end. And now I promised you to solve Hirota. And as part 3 will have only one slide. So the statement is the following. If Gothic Q and Gothic P are two fuse flags, by the definition of the implies, then this construction solves this equation. So what is here? A is fundamental representation, and this is A star is dual representation, contragradient representation. So if A is fundamental, its dual is also fundamental, maybe some other. So if you have representation as dual, you have natural convolution, and this bracket means natural convolution between representation and its dual. So result is a scalar.
Can you just repeat what?
Yeah. So this is vector. This is covector. A dual vector. So QA is a vector in the A's fundamental representation. For any representation, you construct dual representation. So this is the corresponding dual representation. If you have representation vector in the representation vector in the dual representation, there is a convolution, which is a number. Invariant transaction of group action. This invariant, think about it as the volume if you wish, it's our T function. And the claim, if Q and P are fuse flags, then T solves Hirota. Proof is very simple. the difficult part is normalization, maybe. And now, if you just identify P with Q's with some special shifts, what we can achieve that for negative S, T function is 0, and then it has meaning of transfer matrices in spin chain. And from point of ODM, this construction has very simple meaning. So if you have our plane of complex parameter X, we have many stock sectors. And we take our small solution here and take monodromy here, and the distance between them is S plus H. Monodromy from here to here projected.
H
Is a Coxeter number. So we start from the solution which is small in this stock sector, and we consider its monodromy to the another stock sector, which is S plus H rotations away, projected to the minimal solution there. Coefficient of projection is T. So TIS is this monodromy. This is what the meaning of the formula. Okay. Okay. And now part 4, I will at least give you some intuition what is happening here. So let us consider this case of SLN when we have embedding of lines. So depending on how we choose, so what is the statement? If you take SL4, we have 1 forms, 2 forms, and 3 forms, 3 fundamental representations. So first, you can consider this Coxeter head function. So 0, 1, and 2. It means that line shifted by 2 units of shift is embedded in the plane shifted by unit of shift is embedded into the 3-dimensional plane not shifted. But we can also take a different height function, and this still be embedding, and so on. So this is one flag, this is another flag, this is a third flag, and they fuse together. That's why we call it fuse flag. Okay, and but how we can write it differently? So this is line embedded in this 2-dimensional plane, and this is line embedded in the same plane. But these 2 lines generically are different lines. So what we write here is that Q2 plus up to normalization is Q1 plus plus wedge Q1. So this is QQ relation. Okay. This is not literally, but it can be reduced to QQ relation. So this is what is the meaning of this construction. And for this series, there is interesting fact that on the right-hand side here, we have Dirac spinor. So this is a spinor representation. And condition of them being on group orbit of their highest weight makes from them what is called pure spinors. So physicists call it pure spinors, which in this language, it's just orbit of highest weight. Okay, and pure spinor condition, psi gamma psi equal to 0, is Plücker condition, the Plücker quadric. And then what can be shown from this fuse flag or from ODM business, that all the other Q functions which have here are obtained by fusing 2 spinors with gamma matrices with some particular shift to spectral parameter. So the message for the D series, we can actually contract all the Q functions entirely from spinors. And how we use it? So my original goal, I did not say it at all today, let me say it now, was to solve spectrum of certain spin chains. For spin chains, these vectors Q have very specific analytic properties. There is some very concretely fixed prefactors through Greenfield polynomials, some function. Non-trivial part, I mean, this is of course non-trivial part, but then we require that it multiplies by some polynomial and spectral parameter. So the question, using this ansatz, can we satisfy the fuse flag condition? And the answer, there is only finitely many ways to do it. And this precisely the spectrum of the spin chain. We can do it by solving Bethe equations, but also we can do something different. We can take our pure spinors, generate everything from them, and then satisfy this condition. So in reality, we've shown that these 2 Wronskian equations with finite Wronskian can replace fully Bethe equations for SO2R series. And by asking that these equations are satisfied by these ansatz, functions with these ansatz, we crank the numbers and be able to find like first several thousands explicit solutions for SO8 and SO10 spin chains. Why SO8? Because SO6 is A series. So SO8 is the first example when it's really D series. And well, if you ever try to solve Bethe equations, you know that it's by order of magnitude more that you can do compared to solving Bethe equations actually. So these are solutions in algebraic numbers of Bethe equations using this technology. So we can do length 7 in vector representation, find 1456 solution in 1 hour, half an hour. So this is how this method is efficient. And this is practical application. Okay. Okay, so now maybe to summarize, starting from linear problem, we found a way to encode relation between Q functions in a geometric fashion. So through the fused-slug condition. This fused-slug condition does include QQ relation. You can prove that it's equivalent to QQ relation, but its power to look at it very differently. If you look to it very differently, you can take, for instance, spinors and encode all Bethe equations just through spinors. And this gives me a much more efficient way to find spectrum. Okay, so thank you. Yeah.
Just a very quick one. So you said that these are the QQ relations. Now these are vector relations.
Yes. So of course I was very fast, and it's kind of
just a small comment on that.
Yeah. So it's quite important. Yeah. First this one. Okay. So Q1 is a vector who is Q11 E1 plus. Okay.
The basis in the representation.
Yes. In the way it's in the standard basis. Yeah. And this is, I need also one more. So from your perspective, this will be Q plus, and this will be Q minus from your talk. And from here, you just take Q2, you just take the very first one, Q1, Q21, E1 wedge E2. So if you take 1-2 component of this relation, you get that Q21 is given by Wronskian determinant of Q plus and Q minus. This is an example of QQ relation.
So what QQ relation then? And you know what is it?
Okay.
Psi system.
Let's do it this way.
Okay.
Yes. Yeah. So I mean, you can also do the same for psi. I mean, you have it in your paper. Yeah.
No,
Yes. Yes.
Okay. Yeah. Well.
So it's like a psi system. First component gives you standard QQ relation. No, I mean, psi system related to the origin gives you QQ. Yes. And first component gives you QQ relation. The point that you do not oblige to go to the first component, you can to other components. You actually the whole ecosystem there. And this ecosystem has certain symmetries, so you can use it for your advantage.
For the productivity, it's a closed system anyway.
We can discuss in private. Yeah, this is a point. It's closed, and it's formally sufficient. But if you start massaging the game, you find new ideas and which are more efficient.
I want to understand what you mean by massaging.
Okay, yeah. So it takes.
Yeah.
Yes.
Okay, thank you.
So you have a Steve?
Yes.
So about that, so you want to solve the
Yes.
So maybe I don't know. It's a lot of function. From a bunch of them, you want to get all of them.
Mm-hmm.
And how difficult is it? I mean, because you're starting in the ODE case where you want to find an entire function from another entire function on some functional array.
Mm-hmm.
And this mathematically probably quite big. But maybe in this polynomial case, more simple, I mean, simple, like linearity instead of something.
So what I'm claiming here, after the talk, we can discuss in detail what it means. So I can, it's possible to replace QQ system that you know with these equations for D series. Okay, is it simpler or not? Well, for polynomial solution, yes, and also it's much more covariant. So, okay, what I'm saying here is the following fact. Instead of QQ relation, you can do this. And if you solve this, you're done. Everything else follows rational combinations. So it's you may want to look at it. And it may be, if you look in detail, maybe it will be useful for concrete solution. Yeah.
Okay. Thank you. Any more questions?
Mhm.
No, let us thank Dmytro.
Mhm. Mhm.